Hey guys, so I'm Matthew, and this is the first video, and hopefully a long list of videos. And what I'm going to do is catalog my math journey. I'm currently a junior, and I'm taking pre-calculus, but I have taken it upon myself to learn some higher level mathematics and science. And today we're going to go over a basic calculus concept, right? So in calculus, there are really three major tenets, and those are the limit, the derivative, and the integral. There is obviously a lot of other stuff, but those are like the three. It's hard to call them basic, but three fundamentals of calculus. And today we're going to be talking about the integral. So we're going to walk through what an integral is. And again, when I say what an integral is, I mean what an integral is to me. I've tried to watch like some courses on real analysis and stuff to like really get a rigorous idea, and I can't follow it right now. That's just too above my pay grade. So what I'm going to do is explain what an integral would mean, and explain any concept that I'm learning that's at my level right now, and kind of how I interpret it and how you should probably interpret it if you're learning along with me, or if you're going to learn this stuff, or if you're just reviewing what it really needs to mean to us. So first of all, let's write down the integral. That right there is an integral. Pretty terrible, but if you stick along for the ride, you'll come to find that my handwriting is not exactly a work of art. So what does this mean? Let me actually draw a nicer one, because I can't bear to stare at that. Okay, that's a little nicer. So this big S, and because it is an S, it's archaic. And the Germans used this pretty big S. I forget if it was a capital S or what the deal was, but they used it, right? I think it was to stress. And what it pretty much means is it means sum, right? We're finding the sum. So now, you might have heard of this thing called summation notation. And the eraser just fell off. This other thing. And this is sigma, right? But we don't really have to worry about this guy yet, right? We're talking about a different sort of sum. And mind you, this integral sum, right now, the way we've written it, is a general integral, right? It's called an indefinite integral. That's what we refer to it as. It is no lower or upper bound. Now, again, to someone else, it might have a lower or upper bound. Maybe in real analysis, we learned that this is something and that is something. But for our level, for the level of you're just learning an integral, this is what we call an indefinite integral. That's all that means. Now, let's work on solving a very simple indefinite integral. And to do that, let's learn a very simple rule of the indefinite integral. So let's say let's literally just integrate x. So one thing to note when we're integrating is we write this integral symbol. Remember, this just means sum. We'll talk about what we're summing later. The integral of x, and we always need to write dx. And I'm going to be completely honest, I still do not fully understand why we need to write dx here. What we're really saying here is a really small value of x, but I don't get why we need to write it here. Because you need to write, what we're really saying is integrate x with respect to x. But I still don't know why we need to write that. So, with that being said, let's talk about a very simple rule of integrating x dx. So, let's say that, because what we're really saying here is x to the 1, right? X to the first power. So, to solve this, we actually need to learn a rule. So, let's generalize this to x to the nth power, right? If we're integrating this, what does this mean? Well, this is actually going to be x to the n plus 1 divided by n plus 1, right? So let's apply that. So let's say we're simply integrating x. So x to the 1 dx. What should this be equal to? X to the 1 plus 1 divided by 1 plus 1, which is going to give us x squared over 2. And boom, we integrated. So the integral of x to the first power is equal to x squared over 2. But we're not done. Whenever we're integrating an indefinite integral, we always need to add plus c. And engineers sometimes use plus k, I believe, for reasons I don't quite grasp. But in general, in mathematics, we see a plus c, and that just means plus some constant. Because what we'll come to find when we graph these things is that the constant, when we're taking the derivative, the derivative of a constant is just 0. So when we're integrating, which is virtually the opposite, and again, just this is my understanding, right? So this may be wrong, but at our level, it's virtually the opposite, right? So when we're integrating, we need to add plus c, because the derivative of a constant, derivative of 4, for instance, is 0. So when we're integrating, we don't know if there was a number. So we need to add plus c just in case there's a constant, because it doesn't affect our final answer. So we need to do x squared over 2 plus c. Obviously, the nitty-gritty here is x squared over 2, but we cannot forget the plus c. It's integral to our answer. Yes, that was a pun. I'm sorry. Okay, so now let's try to make this work in a little bit of a broader context. Or rather, not a broader context, but I'll let you in on a secret. Right now, I am taking physics. Just physics. Not AP physics or anything like that, just physics. And one of the things that we learn is that velocity is equal to displacement over time, right? So what we're really saying is that velocity is equal to the change in displacement with respect to time. Now, we could write dt, I guess, right? Because what we're saying here is the velocity is equal to change, because this thing is called delta. You may or may not have come across this yet, but delta just means the change in. So the change in displacement with respect to time is equal to velocity, right? So let us attempt to apply that in a physics problem. So let's say we are a physicist, and we have a velocity time graph, which I'm sure you guys are very well acquainted with at this point if you're watching this video. And let's say we get a function like that, right? So velocity is whatever it is. We're really worried about the x-axis here. Now, you're a physicist, and you want to find the total displacement here. Total displacement. So when I say total displacement, I mean in a certain range, right? So let's say from t equals 0 to t equals 4. That is a horrendous 4. I'm sorry. Okay. So we want to find t equals 0 to t. That's even worse. Okay. T equals 0 to t equals 4. And we want to find this, the area under the curve, because the area under the curve actually yields the total displacement from t equals 0 to t equals 4. And let's say, and again, let's keep this very simple. Let's say we have f of x is simply equal to x squared, right? So that means that velocity is increasing. But it's not constantly increasing, which might be new, especially if you're taking physics, like not AP physics, just regular physics. And I think even in Physics 1, you'll always see constantly increasing. But no, this is not constantly increasing, which is why we have this curve thing going on. So we want to find this displacement, right? Because again, what we're really saying here is that from 0 to 4, to find this variable, it's the displacement, the total displacement, which is this shaded area, over time, or with respect to time. That is what yields velocity. And just think of it like this. Let's say you move 5 meters, and you do it in 2 seconds. From that, you can get velocity, and that's exactly what this is. We can find the total displacement, put it in respect to time, and in doing so, we yield velocity. And I hope I've kind of hammered that point home, and we fully understand what that means. So what we would have to do to solve this is make our integral. So we have this bad boy, and so we want to integrate x squared. But we want to integrate x squared from 0 to 4. So this is our lower bound. We put it at the bottom, and our upper bound is 4. And we need to write dx. So the very first thing we need to do is treat this integral as indefinite. So forget about the upper and the lower bound. Forget about 0 and 4. We need to find the indefinite integral of x squared. So let's rewrite that. So just simply, let's focus on x squared dx. So this is equal to, from the rule we saw earlier, x over 2 plus 1, 2 plus 1, which is going to yield x cubed over 3. And remember, we need to add plus c, right? Plus some constant. Now what we do, because we're almost there, so now what we do with x cubed over 3 is we plug in our upper bound and our lower bound into x, right? So we have x cubed over 3. So we get 4 cubed over 3 minus our lower bound of 0. And remember, we're plugging this in for x. 0 cubed over 3. And this is simply going to yield 64 over 3. So the approximate area under this curve, the total displacement, is approximately 64 over 3 units. Now, so just soak that in for a second. So what we're really saying here is that to get the total amount of velocity, let's say z, right? So to get to z in 4 seconds, it takes us 64 over 3 units of displacement with respect to t equals 4 seconds. If so, hopefully that makes sense. And that yields z, whatever that might be, that yields z, which is our velocity. So now we're going to go over one more concept, and this is kind of going to revert back to, this is more, so I wanted to first do an example just to kind of, so we kind of understand what the integral is all about. Because at least for me, one of the things I always ask in mathematics is, why is it useful? What does it do for us? And I hopefully just gave you guys a decent example as to how exactly we can use the integral in a useful manner. So now what we're going to do is talk about that thing I was talking about earlier with the s, the sum. So let's say we want to find the sum. Or not find the sum, but let's just talk about what the integral is. So back to this guy. So we talked earlier about how this is just the archaic version of German S, and it stands for sum. Now you might be wondering, the sum of what? So let's say we have some graph. Now, if we have a graph like this, right? Just pretend like that's a straight line, and I'm not horrible at drawing. If we want to find this guy, this is just a triangle, right? So let's say we have an x and we have a y. We could just use the Pythagorean theorem, right? But let's erase that. And now let's say we have like this. I'm going to want to find this guy, right? So what we need here is to use integrals. So the sum that we're going to use, or what we're finding the sum of, like what are we summing, right, is, like how do we get 64 over 3, for instance? Well, what we did was we actually made an infinite number of rectangles. So if you see these rectangles I'm drawing, they're clearly not beautiful approximators of the total sum, but simultaneously you can kind of understand where this is going, right? So we have these rectangles, and if we take the area of those rectangles and we add all of them up, and if you see over here, the smaller the rectangles are, sorry, I know it's not really focusing, but hopefully you can kind of understand this idea. The smaller the rectangles are, the thinner they are. As the thinner and thinner we make these rectangles, the closer and closer we get to our actual value, right? Because what we're doing here is we're taking the area of every single one of these rectangles and adding them all up. And that is going to be very close to the total area under this curve. And if we want to get closer and closer, we make thinner and thinner rectangles, right? Because let's say we actually try really hard to make thin rectangles. And this is going to be the last thing we speak about for today. So let's say we have that, and we want to make really thin rectangles. So so I'll stop there, but you see what I'm talking about. There's very minimal space left. And our plan is to make these rectangles so thin that the amount left over is simply just it's so small it doesn't matter, right? I'm kind of blanking on the word. My physics teacher loves to use it, but I'm forgetting the word now. But it pretty much means that it's negligible. That's the word, right? We want the area to be so small that it's negligible. And yeah. So just to quickly recap, the integral is the sum of a lot of small rectangles under a curve. So if you want to find the shaded area next time, all you need to do is find a function, f of x equals something, and then just integrate that something from a to b. And that will let you find the, let me write this in a more generalized format. So if there's one takeaway, and if you're watching this and you want to learn the generalized point of the integral from a to b of a function, a to b of some function, let's just put z. I don't mean to have z as a variable. Z just represents some function. With respect to z is going to yield the area is going to simply be area under curve of our graph from A to B. There's one thing to take away, it's this, right? For our lower bound A, lower bound B, integrating a function with respect to a variable in question equals the area under the curve of that function of our graph from the lower bound A to the upper bound B. Thank you.